Good morning, welcome to new lecture on modulation, and in this lecture we will be talking about pulse amplitude modulation and quadrature amplitude modulation. Okay. So, let us start with examples of modulation, and we have already seen the basic equation for modulation is this, where ST is complex spaceband signal, Bn are the coefficients of this complex spaceband signal. In general they can be complex, and this Pt minus Nt is the basic pulse that we use, right. So, in the last lecture we have discussed what should be Pt to avoid intersymbol interference. Okay. So, this equation describes basic linear modulation, and we have seen that modulation in general is the way how can you go from binary sequence to waveforms. You should always remember the basic underlying theme that we are discussing. This is what the modulation is, right. So, we have seen various examples of modulation before. For example, we have seen unipolar modulation, polar modulation, bipolar modulation. In all these modulation schemes, what happens? So, based on the binary sequence you choose this Bn, and Bn is modulating the pulse. All these examples of the modulation schemes that we discussed, unipolar, polar and bipolar, falls into the category of pulse amplitude modulation, right. What is pulse amplitude modulation? You have a basic pulse, and the amplitude of this basic pulse is modulated by Bn, and there are various ways in which you can choose Bn based on the binary sequence. All these examples are examples of pulse amplitude modulation. In modern times, there is very popular ultra wide band modulation scheme, which is also an example of pulse amplitude modulation. The only thing that is in there, that this complex spaceband signal that we use runs in over multiple gigahertz. So, this is a very wide bandwidth signal, but that is also the example of pulse amplitude modulation. And it is a good idea to start thinking about pulse amplitude modulation, and from here we can go to other modulation schemes. Okay. So, let us see what happens in modulation technique. We can consider the blocks of B bits. For example, suppose this is the binary sequence that we have, and this binary sequence can be converted into blocks, and here we have considered the blocks of 4 bits. Okay. So, this is one block, second block, third block and fourth block, and now these blocks of bit can be converted to a symbol. And what is a symbol? Symbol is nothing but it is a quantized real number. Okay. Here what we have done is we have just considered the symbol which is equivalent to the binary value of this block. Okay. For example, we can map this to a number 10, this to number 15, this to number 1 and this to number 9. So, first step in modulation is you convert these bits or blocks of bits into the symbols. Bn are the symbols. Okay. So, we have converted this binary sequence into 4 numbers or 4 symbols. All right. So, if we have blocks of B bits, how many symbols you can have? You can have 2 to the power B symbols. This also we have seen when we discuss quantization, right. So, for example, if we have B binary bits, then the number of symbols that you can have is 2 to the power B. Okay. What will be the symbol rate? For example, if I have a bit rate RB, which is number of bits per second, and in this example that we have considered, for every 4 bits I have a symbol. So, symbol rate, which is number of symbols per second, is nothing but it is the number of bits per second divided by the block length, which is in this case B, is not it? And number of bits per second is nothing but it is the bit rate. So, I get a very neat expression that is relating the symbol rate and bit rate. So, we can say that the symbol rate is nothing but it is the bit rate divided by B, because for every B bits you are going to have one symbol, right. So, this is the relationship between symbol rate and bit rate. If B is 1, that means for each binary bit I will be generating a symbol. Then we are in the regime of binary pulse amplitude modulation. If B is greater than 1, then I am talking about multi-level pulse amplitude modulation, or in short we can say it as MPAM. Okay. M stands for multi-level pulse amplitude modulation. For example, if B equals to 4, then we are talking about 2 to the power 4 PAM, which is 16 PAM. Okay. So, M represents the number of multi levels that you have. So, if B is 4, the total number of symbols that we have is 2 to the power 4, that means we are going to have 16 symbols. Okay. Let us now look at the signal constellation for MPAM. So, this is the signal constellation of MPAM, and what we are showing is that we are putting the symbols on the real line. So, in pulse amplitude modulation, the signals are confined to be real signals. Okay. So, the symbols that we have can only take real values. Okay. So, this is the restriction. Once you allow the symbols to be complex symbols, then from PAM we go to quadrature amplitude modulation, which we will discuss after we have finished with PAM. But for starting we are talking about PAM, and the basic restriction in PAM is that the signals are considered only to be real signals, okay, or symbols are real symbols, and we are plotting the symbols on this real line. Symbols are quantized discrete time signals, and in literature these symbols and signals are used synonymously, and sometimes we also refer to symbols as signals. So, please do not get confused. So, for example, one symbol can take a value of d by 2, another symbol can take a numerical value minus d by 2, all this is real. Next symbol can be assigned an amplitude of 3d by 2, and so on and so forth. Interesting thing that you can look in here is that the symbols are separated by a constant distance d. For example, the difference between the two symbols is d, the difference between these two symbols is also d, right. So, symbols are at least separated by a distance of d, and this we will see in a while, and this will become more clear when we discuss detection, that the performance of any modulation scheme depends upon this minimum distance d. Okay. So, to ensure that your modulation schemes achieves a certain error performance, you want to make sure that the symbols are separated by a certain distance d, okay, and this has to be mostly uniform. How do we choose d? So, we can choose d as some constant alpha times sigma, where sigma is the standard deviation of noise, right, and this constant depends upon the modulation scheme. Typically, you can choose the value of alpha as something between 5 and 10. Okay. So, what we are saying is, depending upon the noise level and depending upon the some constant which varies from modulation scheme to modulation scheme, you decide on a certain distance d. Okay. And once you have decided on a certain distance d, then what you want to make sure is these symbols are separated by distance d, okay, or the minimum distance between any two symbols is at least d. And once you have decided for that, you can easily draw the signal constellation. Signal constellation is just drawing the signal alphabets. So, we are just drawing the amplitude levels of various symbols that we have. And what is this idea behind choosing a certain constant d? For example, if you want to look at the error performance of this modulation scheme, what would happen is the possibility of error is coming only from the neighbors. For example, suppose you are transmitting a symbol, the error may happen when your receiver confuse this symbol with one of the neighboring symbol. So, you are transmitting let us say symbol A, the receiver might confuse it with a symbol B or symbol C. The symbol B and symbol C are the neighbors of this symbol A. The possibility of receiver confusing it with symbol D is very remote. Why is this so? Because for receiver to confuse A with D, the noise amplitude levels must be larger than the noise amplitude levels that would create confusion for the receivers confusing A and B. Okay. For example, if this is the distance between A and B, and let us say if noise amplitude levels are larger than the half of this distance, then the receiver would confuse A to B. And if the receiver has to confuse A to D, then the noise amplitude levels has to be larger than half of the distance between A and D. Okay. These things will become more clear later on. But the point that we are emphasizing is that receiver is most likely getting confused from the neighbors, and thus for the error performance it is only important that we maintain a certain minimum distance between any two symbols. Okay. So, we want to make sure that the distance between any two symbols is greater than certain threshold. And you can also see this from the noise characteristics. We have already seen that the noise is Gaussian, and this is the probability density function of the noise. On the x axis we have the amplitude of noise. So, it is very clear that the probability of higher noise amplitudes decreases rapidly, and hence the error contribution is primarily from nearest symbols, because it is very unlikely that the noise amplitudes are so large that A gets confused with D, right, because the probability of larger noise amplitudes is smaller, and thus most likely receiver gets confused only from the nearest symbols or nearest neighbors, and thus it is only important to separate the symbols at least by a certain distance D. So, what happens in signal constellation design, let me go back to that signal constellation design, is you choose a value of D, which you can choose depending upon the standard deviation of noise and some constant. Once you have decided upon this value of D, you can place all the symbols separated by this distance D, okay, and by this you can get to the signal constellations of M-PAM. So, let me repeat, what is PAM? PAM is the linear modulation scheme in which the symbols are modulating the amplitudes of the pulse, and these symbols are confined to be real symbols. Okay. Once they are real symbols, you can just draw them on the real line, and M denotes the number of symbols that you have. For example, in this case we have M symbols, and thus we call this as M-PAM. Let us look at the average symbol energy. So, how can we find the symbol energy? Symbol energy we already have seen in one of the lectures, that energy is nothing but distance square. So, if we consider the signals as vectors, the energy of the signals is nothing but it is the distance of the signals from the origin and square of it, is not it. So, this is how we interpret the energy of the signals or symbols. Suppose I have two symbols t by 2 and located at minus t by 2 with a distance of d. What is the energy of this symbol? It is d by 2 square. What is the energy of this symbol? It is again d by 2 square. And what is the average energy? So, there are two symbols, thus we divide by 2. So, this will give me the average symbol energy of this constellation, right. Similarly, I can find the average symbol energy of this constellation. Here the difference is that we are having M symbols. So, we have t square by 4, which corresponds to the energy of this symbol, plus 3d by 2 square 5d by 2 square and so on and so forth up to d square m minus 1 square by 4. And then I have to account for these negative symbols, and these symbols have the same energy as these symbols. So, I just have to multiply by a factor 2 and dividing by the total number of symbols that I have. And then it is just arithmetic. You can reduce this to this, the number of symbols is m, and then we get a neat series like 1 square plus 3 square and so on and so forth up to m minus 1 whole square. And we know that sum of this series is nothing but m into m plus 1 into m minus 1 by 6. Solving all this out, what we get is average symbol energy is d square by 12 times m square minus 1. And I request you to remember this formula because it is an important formula and it denotes how the average symbol energy varies in ampam. Okay. So, the average symbol energy in ampam is d square by 12 times m square minus 1. Let us work it out little bit more. So, we have said average symbol energy is d square times m square minus 1 by 12, and m we know it is 2 to the power b, where b is the block length, right. So, remember that we are taking a group of b bits at a time and we are converting this group into a symbol. So, m is 2 to the power b, substituting that in here we get average symbol energy by this expression. And if b is greater than 2, 2 to the power 2b minus 1 can be approximated as 2 to the power 2b, and thus I can approximate the average symbol energy by this thing. And one thing that you should note here is as the value of b increases, average symbol energy becomes impractically large. That means, if I have a large m, then the average symbol energy that you need to invest is quite large, and thus this ampam modulation scheme is not very interesting modulation scheme to use for very large values of m. Let us look at one more thing. Suppose we have chosen d as some constant time sigma. We know that the distance between the symbols has to be chosen such that they are larger than the standard deviation of noise by some constant. Then from this expression, which we have already derived here, substituting the value of d as alpha times sigma, from this expression I can get this expression. So, d is just alpha times sigma. So, Es becomes alpha square times sigma square by 12 and this thing. From this I can get 2 to the power 2b is 1 plus this thing. So, what we are doing is we can write this as from this expression we can get this expression, and then it is straightforward. I shift 1 to that side. So, I get 2 to the power 2b is 1 plus 12 Es by alpha square sigma square, and this is this expression. Taking the log on both sides with a base 2, I will get 2b log 2 is log 2 1 plus 12 Es by alpha square sigma square, and log 2 is 1, and 2 I shift to this side, I get this expression. And this is very interesting expression, the one that we have derived here, because it looks exactly like Shannon's capacity formula with some minor difference. Form is similar. In Shannon's capacity formula, the C is number of bits that you can have per symbol or signal, and here also in B is the number of bits per symbol. There are minor differences in the interpretation of these two formulas. This formula says that if you increase alpha, then you reduce the effect of noise, because what are you doing is you are increasing the distance between the two symbols. If you increase the distance between the two symbols, it is less likely for the noise to create errors, because noise amplitudes must then be much larger. So, by increasing the distance between the two symbols, we can decrease the effect of noise, and thus when I increase alpha, I reduce my bit error rate, but then I also reduce my B. This is what this formula is saying. So, if you want to reduce a bit error rate, the number of bits per signal also reduces, whereas this formula says that if you are designing a modulation scheme or system where number of bits per signal is less than C, where C is the channel capacity, and that is why we use the letter C, then you can make your bit error rate to go down to practically 0 or arbitrarily very small. This is what Shannon's capacity says. So, if you make the number of bits per signal less than C, then you can achieve a bit error rate approximately of 0, or at least of a very, very small value, such that it does not matter. So, this is all that we have in PAM. Remember the key things that we have said for PAM. The first thing that we have said is PAM is an example of a linear modulation scheme, where Bn or the symbols are restricted to be real symbols. Okay. And once you are restricting yourself to real symbols, you can get to a signal constellation only by arranging your symbols on the real line. When you arrange your symbols on the real lines, what you want to make sure is that the minimum distance between the symbols is larger than d, and where d is some constant times standard deviation of noise. And then we have seen that when we have got to that constellation, what happens is that the average energy per symbol grows with the square of m, or it varies as m square, and thus for large values of m, average symbol energy becomes impractically large, and thus we do not use PAM modulation scheme for pretty large values of m. There are better ways to go to multi-level modulation schemes than PAM, and we will see them shortly. Then the second thing that we have covered is we have got a very neat expression of the number of bits that you can afford over a symbol. That depends upon what alpha you choose, where alpha dictates the distance between the two symbols. Namely, the distance between the two symbols is alpha times sigma, where sigma is the standard deviation of noise. So, if we increase alpha, what we do is we increase the distance between the symbols, making the effect of noise go down, thus reducing the bit error rate, but the penalty that we have to pay for that is we cannot have more bits per symbol. Okay? And we will see that why that is important. Okay. So, PAM is basically baseband. So, ST that we have is a complex baseband signal, it is a baseband signal, is not it? Once you are restricting Bn to be real, then ST becomes a real baseband signal, that is it, but it is a baseband signal. And what we want to do is we want to go from baseband to passband, and of course, at the demodulator you want to come from passband to baseband. And there are various techniques by which you can go from baseband to passband. We have covered a lot about baseband to passband conversion, and we will introduce few more ideas in this lecture about this baseband to passband conversion. Some of these ideas you might have studied in courses like in analog communication. So, one idea to go from baseband to passband is to use what is known as double sideband amplitude modulation. It is the simplest way to go from baseband to passband. And what you do is you have a baseband signal and you multiply a baseband signal with this rotating complex exponential, and you get a passband signal. And you know that if the spectrum of the baseband signal is like this, which is centered at around DC, the spectrum of the passband signal would be the same spectrum. Other than that, now this spectrum is shifted to the standard frequency of Fc, and we know that this Fc, the carrier frequency, must be much larger than this B. And we have looked into the definition of bandwidth several times, and we know that by convention bandwidth is the range of positive frequencies present in the spectrum. So, in this case bandwidth is B, because this is the range of positive frequencies, and in this case the bandwidth is 2B. All this spectrum is located on the positive side of the spectrum. So, bandwidth in this baseband to passband conversion goes from B to 2B, and that is bad. In reality, what we do is, you cannot have a passband signal which is complex. This is a complex signal because of this thing. So, in reality what you want to have is a real signal. So, what you do is, instead of multiplying xt with e to the power j 2 pi f c t, you also multiply xt with e to the power minus j 2 pi f c t, and you add these two things up. So, what you get is basically xt times cos 2 pi f c t, but that does not do anything to the wastage of bandwidth that we have discussed. Double sideband based modulation schemes simply converts baseband bandwidth of B to passband bandwidth of 2B, and this is bad from communication resource point of view. And thus what we want to do is, we want to reduce this bandwidth wastage by using either single sideband modulation scheme or quadrature amplitude modulation scheme. Okay. So, let us look at single sideband modulation scheme. So, this is not very important for this course, this is important for the courses like analog modulation. In digital communication we never use single sideband modulation, and thus I will not talk about this a lot. But just for completeness, let us see what is the single sideband modulation. You take in the signal, multiply this with cos 2 pi f c t, you take the Hilbert transform of the signal, and you multiply the Hilbert transform of the signal with sin 2 pi f c t, and you produce a passband signal. This is what happens in single sideband modulation. Take signal, multiply with cos, take Hilbert transform of the signal, multiply with sine, subtract these two components and you get a passband signal. What it does is, it clips off one side of the spectrum. So, this is a double sideband because it has upper sideband and a lower sideband. When this signal is converted to a passband signal, what happens is lower sideband gets clipped off. So, what we end up with in passband is only with one sideband, and this is the idea behind single sideband modulation. So, you only have a single sideband. Remember, in DSB double sideband we are having both sideband presence, upper sideband and lower sideband. In SSB we only have either upper or lower. In this picture we are just showing the upper sideband, but it might happen that you only have lower sideband, and that is the name single sideband modulation scheme. And if I look back to this double sideband modulation scheme, you see that we have a dashed line and a solid line. It simply says that the information in this part is redundant. Lower sideband has the same information as upper sideband because the signal is symmetric, isn't it? If xt is real signal, the amplitude spectrum is symmetric and the phase spectrum is odd, and thus from one side of the spectrum you can easily obtain the other sideband. So, from one sideband you can easily extract the other sideband. So, in reality there is no need to transmit both sidebands, lower as well as upper, because it is redundant, one sideband is redundant, and this what we do in single sideband modulation, we clip off one sideband. Okay. We only have either lower or upper sideband, and this is the idea behind single sideband modulation. Why it is not useful? It is not useful a lot because it requires some sharp filters to clip off one of the sideband, and that is why we do not use this single sideband modulation technique. Okay. Let us now move to quadrature amplitude modulation. In quadrature amplitude modulation, what we do is we take in that signal. So, baseband signal multiplied by this rotating complex exponential, and we add to this the conjugate of this thing. So, we have x t e to the power j 2 pi f c t, and to this we add the conjugate of this. So, we get to a form like a plus a conjugate, and we know what is a plus a conjugate. It is 2 times real part of this thing. So, from this we get this thing is nothing but it is 2 times real part of this quantity, and this can be arranged as real part of root 2 times x t e to the power j 2 pi f c t. And when we have said the passband to baseband conversion, actually this is the equation that we used, and because this is the most important way of conversion of baseband signal to passband signal, because that is using the ideas behind quadrature amplitude modulation. So, even though we have not mentioned it, but if your passband signal can be expressed like this, actually we are in the regime of quadrature amplitude modulation. This is the way of conversion of baseband to passband signal. Okay, and we have read a lot about this, that how can you think about a complex baseband signal in terms of passband signal, or the other way around, how can you think about the passband signal in terms of complex baseband signal. And we have already seen several equivalents between this complex baseband and passband signal, namely that the inner product of passband signals is the real part of inner product of baseband signals. We have seen that the energy of the passband signal is the same as the energy of the complex baseband signal, and to make that equivalence we have introduced this scaling factor of root 2. So, if you have forgotten about this complex baseband to passband conversion, I request you to look again at lecture number 19, 20 and 21, where we have dealt in detail about this equivalence of passband and baseband signal. Okay. The one picture that is important in this context is, if I have a complex baseband signal, it is complex, that is why the spectrum is not symmetric, and because this spectrum is not symmetric, it has no redundant information present, right. Its upper sideband is completely different from lower sideband, and thus the information is present in both sidebands. And thus for bandwidth, we have also seen this, the bandwidth of this signal should be considered as the total support of the spectrum, including both positive and negative side of the spectrum. And when this is converted to a passband signal, there is no bandwidth inflation, because bandwidth of this passband signal is also B. Thus, if we have a baseband signal of bandwidth B, you can go to a passband signal also bandwidth B, there is no bandwidth wastage. We can also think about this in some other ways. For example, let us say if I have a signal XCT, which is a baseband signal, and let us take it to be a real signal, actually XCT and XST are real signals, and let us assume that the bandwidth of XCT is B by 2, bandwidth of XST is also B by 2, bandwidth of this I channel is B, because there is a double sideband modulation. The bandwidth of this Q channel is also B for the same reason, but the total bandwidth of the signal is also B, it does not add up. Why? because I and Q are orthogonal components, and thus the total bandwidth of XPT is B, and the baseband bandwidth, the baseband components are not orthogonal, is B. Okay. So, this is one idea why we like to use quadrature amplitude modulation. In short, the quadrature amplitude modulation allows for two orthogonal channels, is not it, and thus you can have double the rate compared to the information in one channel, and thus you reduce bandwidth wastage. So, there are many ways in which you can understand this idea of quadrature amplitude modulation. So, what is quadrature amplitude modulation, or sometimes it is known as QAM, QAM in short. So, let us just contrast PAM with QAM. So, in PAM we have a signal which is restricted to be a real signal. In QAM we have a signal which is complex signal, otherwise there is no use of QAM. If ST in the case of QAM is a real signal, then QAM is same as PAM. Okay. So, in QAM the signal ST has to be complex signal, which can happen when this Bn takes in the complex values. And once you have a complex baseband signal, what you can do is you can use this relationship to construct the passband signal from the complex baseband signal. Okay. This expression we have seen before in lecture 19, 20, 21. We have seen all about this I channel, Q channel, orthogonalities of I and Q channel. So, it would be a nice idea to revise them, because actually we were discussing this passband to baseband conversion in the context of QAM. Okay. Let us look at the signal constellation diagram of QAM. In this case, I have QAM with m equals to 4, that means the multi levels in the QAM is 4, that means I am having 4 symbols present. The distance between the two symbols has to be again some constant d. So, you have to make sure that the distance between any two symbols is at least d. Okay. So, in this case we are making sure that the distance between any two symbols is at least d, right. So, we have 4 symbols, one symbol can be 1 plus j. So, this is 1 plus j, this is 1 minus j, this is minus 1 plus j, and this is minus 1 minus j. So, I am allowing for 4 complex numbers. Let me write that expression again. So, the passband signal is given by so this is I channel, Q channel, or this is also known as in phase and quadrature phase component. Q stands for quadrature, I stand for in phase. And so, in the in phase component I have SCT, and in quadrature phase I have SST. Okay. So, here I am drawing two orthogonal axes, one along cos omega Ct, which corresponds to I channel, and one along sin omega Ct, which corresponds to Q channel. And then this I channel or cos omega Ct is modulated by SCT, and SCT can take two amplitude levels, 1 or minus 1. Similarly, ST can take two amplitude levels, 1 or minus 1. So, if I have SCT taking in two amplitude levels, 1 and minus 1. So, SCT is along this, SST can take two amplitude levels, 1 and minus 1. So, what can happen? If SCT takes in a value 1, SST takes in a value 1. So, I have 1 plus j, I get to this symbol. If this take this value, this take this value, I get to this symbol. If this take this value, this take this value, I get this, and similarly if this SST take this value, SCT take this value, then I get to this symbol. So, in short I get to 4 amplitude levels. Now, I can look at COM where M is 16. So, again you can think of this as SCT taking in the 4 amplitude levels. Again the distance between the amplitude levels is 2 and this distance is kept constant, and similarly SST can take in the 4 amplitude levels. Now, based on the combination of the amplitude levels of SCT and SST, you can have 16 amplitude levels. So, 4 times 4, 16 combinations. So, you have the 16 symbols, and the minimum distance between any two symbols is also same and constant in this case. And this is the constellation structure of 16 COM. And if you look at this constellation grid, you can see that this is a square grid, and this is the standard constellation structure of COM. Okay. So, COM constellations basically are square grid constellations. All right. Somewhat non-standard constellation is where M is 2 to the power b, and if this b is odd, for example, if b is 5, you get to 2 to the power 5, which is 32. So, in those kind of modulation schemes, you cannot have a square grid constellation. For a square grid constellation, you need to have b as even. If b is odd, we cannot have a square grid constellation, and then you have cross constellations, something like this. Okay. So, in COM we can have square grid constellations, which is the standard constellation for COM, and you can have other constellation structures for COM like cross constellations and so on and so forth. Let us now look at the energy per symbol in COM, and the way we want to do this is we want to interpret COM as 2 real PAMs. So, if you look at the waveform for COM, you can think of this as 2 PAMs. So, there is a PAM here, this is the waveform corresponding to PAM, and there is a PAM running in here, is not it? So, PAM which is double sideband modulated. So, PAM is always real. So, I can think about the quadrature amplitude modulation as 2 real PAM, and if in this PAM I have m dash symbols, and in this PAM I have m dash symbols, then the total number of symbols in COM is m dash times m dash, which is m. M is the total number of symbols. So, m is nothing but it is the square of m dash. That is one important idea, that if we want to think quadrature amplitude modulation as 2 real pulse amplitude modulation systems, if pulse amplitude modulation systems are built to support m dash symbols, then this COM would have the total number of symbols as m dash times m dash. So, total number of combinations would be m dash times m dash, which would decide the number of symbols in COM. From this we can get energy per symbol in COM by first considering what was the energy per symbol in PAM. Energy per symbol in PAM was d square times m square minus 1 divided by 12. Because in COM I am having 2 PAM systems, energy in COM would be 2 times the energy in PAM, is not it? Thus, the energy per symbol in COM would be 2 times, because there are 2 PAMs running in, the energy of one PAM. Energy of one PAM would be given by this. One PAM is supporting only M dash symbols. So, energy of one PAM is this, the number of symbols in PAM is M dash. Thus, from this I can easily get the energy per symbol in COM. M dash square is M, and the energy per symbol in COM thus reduces to d square by 6 times M minus 1. So, we have easily obtained the energy per symbol in COM. Let me do one exercise before we conclude this. Let me take a simple COM modulation, let us say 4 COM, and let us take 4 symbols because it is 4 COM. Let me assume that the distance between the symbols is d. So, this symbol would be d by 2, d by 2, this would be d by 2 minus d by 2, and similarly you can obtain the values corresponding to other symbols. Energy of all these symbols must be same. So, if I calculate the energy of one symbol, that would be same as the average symbol energy. All these symbols have the same energy. It is a square grid constellation where M is 4. So, energy of one symbol is d by 2 square plus d by 2 square, which is d square by 4 times 2 d square by 2. So, you can quickly estimate the energy in the COM systems, and if I use the formula which we derived, which is d square M minus 1 by what was it 6. So, we get M as 4, we get d square by 2. That means our formula is working and is correct, and it can be used to estimate the energy per symbol in even higher modulation COM systems, where calculating energy will be not so simple as in this case. So, let me try to summarize this lecture by presenting the key ideas that we have developed today. One thing that we have said about PAM and COM is that PAM restrains itself to having real symbols. What happens to this PAM when we do this baseband to passband conversion using ideas like double sideband modulation scheme? There is a bandwidth inflation by a factor 2. You can avoid this bandwidth inflation by using the modulation technique known as COM, where you allow the baseband signal to be a complex baseband signal, and you modulate the in phase component of the baseband signal with cos carrier, and you modulate the quadrature phase component of this baseband signal with sine carrier. That will avoid the bandwidth inflation. Okay. The second idea that we have developed is we have covered the average symbol energy that is required in PAM versus COM, and if you see this, it will be extremely clear why this PAM should not be used for large values of M. In PAM, the average signal energy scales as M square, whereas in COM the average signal energy scales as M, it linearly increases with M, but not as a square of M, and this is a significant saving. So, if you want to minimize the average symbol energy, you should use COM where it scales only linearly with M, whereas in PAM it increases as the square of M, and this is not good. In next lecture, we will continue with this differences between COM and PAM, and we will introduce some other modulation schemes as well. Thank you.